Yeah, okay, so I will consider Riemann-Hilbert mostly in the dimension 1, which means for curves for illustration purposes, but it will explain the general idea. So I recall you that classically, if we start with a complex curve, and we consider the category of vector bundles, well, in algebraic or analytic, or there are many possibilities for that. So it's vector bundles with connections, automatically flat. So then Riemann-Hilbert correspondence roughly establishes equivalence of this category with the category of local systems on X. So we can add some additional data as we will. So in particular, we can ask for a special behavior of the connection and the finitely many points. And so that will change the category of local systems a little bit. We can upgrade this to the category of holonomic d-modules. In the case of curves, basically we allowed just d-modules supported at finitely many points, and this can be upgraded to constructible sheaves. In dimension 1 they are flat, so there is no curvature. Okay, so that's okay. Well, say algebraic. So what is here? It's not even a statement. It's just a general idea. So I will give a statement, an example of such a correspondence later on. So this is a motivational part of my talk. So the question is how symplectic topology, so it's homological mirror symmetry seminar. Yeah? Okay, so how symplectic topologists can think about this correspondence. So let's call the side where we have connections, so the modules, let's call it the RAM side of the Riemann-Hilbert, and this topological side, which is basically representations of the fundamental group of X, let's call it the Betti side. So how, for example, symplectic topologists can think about the Betti side? So for that, let's consider somehow coordinate-wise connection. Let's write it something like this. Yeah, this is connection matrix, and let's put a parameter here, h, Planck constant, and let's consider the limit as h goes to 0. Then this term disappears and we get what is known as a Higgs field. So instead of bundle with a connection, we have a bundle with a Higgs field. In other words, we have a Higgs bundle, and having a Higgs bundle, we can construct the corresponding spectral curve, which is, again, let's think coordinate-wise, it's just a characteristic polynomial of zeros of the characteristic polynomial of the Higgs field. So then it sits in the cotangent bundle. So of course, since our cotangent bundle is a complex symplectic manifold, non-compact, so and the spectral curve is a Lagrangian subvariety, not necessarily smooth in general. Okay, so now, so this is a picture. So this is something like sigma, this is x. So then we can play the game which symplectic topologists like to play. We consider a family of Lagrangians which are cotangent fibers. And thinking of the Fukaya category of the cotangent bundle, somehow defined, we can somehow means that, for example, we can take the real part of the holomorphic symplectic form, or we can rescale it, which we will do later. And so we can consider the family of graded vector spaces, so just let's forget about the grading vector spaces. And so this family, it's a locally constant sheaf, at least if x is generic. So, and this is what we can put on the Betti side of Riemann-Hilbert correspondence from the point of view of a symplectic topologist. So then instead of the category of local systems or category of constructible sheaves on X as it appears, we can take the Fukaya category.
If I have a general flat connection, how do I generate it to a Higgs field, and how does it recover the flat connection?
No, okay, so that's a good point. I'm not saying that I give a sort of an alternative proof of Riemann-Hilbert. I put the Riemann-Hilbert correspondence in a different context, which I explain. So if you have just a connection, there is no way to associate to it a spectral curve. But if you have this H connection, then we can do this. So,
So you want to have a Betti understanding of X field?
I want to have a Betti understanding not of the Higgs field but of local systems. So what I'm saying that this is just not the right way to think that on the Betti side of Riemann-Hilbert we have constructible sheaves. It's just a coincidence, because the Fukaya category of the cotangent bundle can be often computed in terms of constructible sheaves. But in general, we should put an appropriate Fukaya category. And next I will discuss what should we put on the de Rham side. Okay, now it's an interesting question. This works. Okay, so that's, yeah, I should not remember.
Any kind of non-appeal a hard theory involved here.
No. So no, or at least not yet. So in the future, we should think of this Planck constant as a twistor parameter, and then indeed there will be not just a single correspondence, but a bit more. And we can speak about twistor family of Fukaya categories, but it's not what I plan to talk about today. So today is sort of a very elementary, it's just 1 hour.
I'm still confused. Do you have this arm in this Fukaya category, and this arm depends on X, but why do you say it's a local system instead of the infinity vector bundle?
It has a flat connection because the Floer homology is Hamiltonian isotopic, invariant with respect to Hamiltonian isotopy, and fibers are the cotangent bundles. If you move. Okay, so let's now discuss the de Rham site. So it was Betty. Again, it's still sort of a motivation, and then I will discuss some more precise example. So the Rham side, again, just at the level of motivations. Well, that is relatively easy, because instead of differential operators on X, we can pull them back as a subalgebra in the sheaf of micro-differential operators on T star of X, or better, we should consider deformation quantization. It's a star product. Of this symplectic, complex symplectic manifold. So then let's think of it as a family of algebras depending on H, non-commutative algebras if we take global sections. So this is a framework of deformation quantization. So
You mean you view otherwise the differential operator?
well, this is bigger than differential operator. It's rather a pseudo-differential operator. It's serious. It has the star product, and the subalgebra of differential operators is closed. Actually, because it has only polynomial growth at infinity. So, and therefore, for every pair of pseudo-differential operators, which are just finite collections of functions, we have some finite expression, and we can put H equal to 1, so that in fact what we get is not a formal deformation quantization, but algebraic, although analytic would be also okay. So then, setting H equal 1, we get something which we had before, but this dependence on H, which we had from the very beginning, it's useful because we can define what are holonomic modules, just taking the support of the finite type module over this non-commutative algebra, which modulo H is Lagrangian. So that's how it goes. Of course, instead we can just look at the filtrations, look at the modules with good filtrations, take the corresponding associated graded. It's sort of a coherent sheaf. We can take support, and that will be the characteristic variety. So, but anyway, the message is that on the Betty side we have the Fukaya category, and on the de Rham side we had holonomic. At least we should from this point of view, we should have holonomic DQ modules. It stays for deformation quantization, which means modules or the quantized algebra of functions on some symplectic manifold. All right, so therefore, kind of a hypothetical and not precise Riemann-Hilbert correspondence, maybe depending on the parameter h, if you would like, should say that holonomic DQ modules it's the same as Fukaya categories. So this is a guiding line, and
Where is the parameter h bar on the right hand side?
so you asking very good question. Thank you. I mean, that's second time, so you should obtain a special prize for that. If you would like to consider everything in families, like if you look here, then the Ram side, it does depend on the Planck constant in general. I set it h equal 1, but a priori it does depend on h, the left-hand side. The Betti side does not, because Fukaya category, it's typical what it will be. It will live over Z, because it's a sort of a wrapped Fukaya. All right. Now, but we can rescale the symplectic form and consider not just a single Fukaya category, but consider a family. Then it will be a family of A infinity categories with respect to the parameter h. And this family will have a monodromy. And moreover, if we would like to incorporate pseudo-holomorphic disks, which will appear later in the story, there will be a Stokes phenomenon. So this is...
So in other words, on the right-hand side, you're just taking the Fukaya category with Novikov coefficients, where you weight everything by symplectic, all the disks by symplectic area.
At the very beginning, there will be no disks. There will be a very simple implementation of this equivalence when no holomorphic disks are present. So then this will be just something living over Laurent polynomials, which is not a big surprise.
When you say monodromy in the family, you mean monodromy in varying h bar? Or?
Yes.
Oh, so h bar is allowed to be complex?
Yes, and it will. Yeah, that's true. Of course, if I consider it in the formal setting, it's just a parameter. Although even in this setting, it's possible to think that h has an argument, but does not.
How do you define Fukaya
So I take, first I even didn't say what kind of Fukaya category. It's better if I explain it in the example, which I'm going to do. But like morally, this is the real part. There is also imaginary part, which I'll take as a B field, but let's forget about it. So then this is it. So we have a symplectic form, and hopefully we can define the rest of the data. Okay, let me, it's better, it's very general. Let's consider an example. So my plan was to consider two examples. One, since you heard, at least many of you heard the lecture of Delin about irregular Riemann-Hilbert on curves, so this will be my first example. And the second example will be holonomic D modules or the quantum torus. it's a different story, because instead of differential equations we will have difference equations, but we will see that this philosophy works nicely in these two cases. Basically, we will do the same thing, but obtain completely different answers. So, first story, or if you'd like, example 1, but it will take some time. It's Deligne-Malgrange Riemann-Hilbert. All right, so let me recall you some notation, data. So again, now X will be a complex projective, smooth curve. I fixed finite subset of points, future singularities, and now a singular term, maybe it's better to call it a regular term. Okay, so kind of in terms of coordinates, it's a negative Laurent polynomial, something like this, or Betti-Puiseux polynomial. Yeah. So, but after some finite extension, we may assume that these are negative integer, or you can say it invariantly as an orbit of the action of some absolute Galois group of the local field, but I will be very precise, kind of concrete. All right. So then, having a curve with marked point, to every point I will assign a collection of such irregular terms, maybe with multiplicities. All right. And having this, we can consider a category of connections, bundles with connections, which have singularities at these points xi, and at the formal level, every connection, which means that if we consider it on the formal punctured disk about xi, it has this Hokuhara-Level-Turitian decomposition. It's kind of a simple exponential d-module tensored with a connection with regular singularities. This is a finite sum over all irregular terms which are associated with a given point. So this is formally. So then, so I consider meromorphic connections on the curve which has a formal type at each singular point with prescribed irregular terms. So this is it. And well, yeah. All right. Now, how to move from this picture to something of the Fukaya type. Maybe I should better say what this Riemann-Hilbert or just recall, I mean, it's part of the Pierre's lecture, but let me recall it. So this Deligne-Malgrange Riemann-Hilbert, so this is what we have on the de Rham side, and on the Betti side we have the category of local systems on the punctured curve, such that if we restrict it on a small circle about the singularity, then this will be a local system with filtration for every direction. Let's call this circle something like this. So for every theta, every direction, we have a fiber of the restricted local system, and it has a filtration, I don't know, vi theta. This filtration is determined, maybe in this notation, probably I should, okay, Ci alpha theta. This filtration is determined by these singular terms, and basically what we do, we consider these functions as they grow as we approach the singular point, and these correspond to the term of filtration, which of the exponent grows faster. So this gives a filtration. Then on this circle, when we move theta, there are some finitely many Stokes points, or Stokes directions, or Stokes rays. When the growth of at least two exponents coincide, and so when we move further, they just interchange. So this is a Stokes automorphism. So all this can be described quite explicitly at the different level of precision. But so if we put on the Betti side this category of local systems with this additional Stokes data, so this is a Deligne-Malgrange version of Riemann-Hilbert, irregular Riemann-Hilbert.
Sorry, just so that I remember, to make sure I understand, on the Betti side, these filtrations have to have some kind of semi-continuity property.
They should have some properties. They should be kind of split, non-canonically split in the generic point. So there are some properties. Yeah, I mean, I am glad that many of you heard a lecture on this topic, so I don't have to repeat it. But you can look. I can give a.
I also did not. So
Mohammed, I think you were no.
I did.
Okay, but anyway, let me give you the reference. There is a book with Malgrange, which is devoted especially to this topic, and there is even nicer book. It's a kind of letters, correspondence between Deligne, Malgrange, and other people involved from going back to 80s. And book of letters. So it's all published. So, but again, the point is that on the de Rham side we have something like D modules, like bundles with connections with some additional restrictions. On the Betti side we have some local systems, again with additional data which depend on the singular behavior. That's all what no, so I have to wait. Now I would like to reformulate the Ram and Betty side, so they will both look like what I proposed at the very beginning. So then let's start with the Betty side, because I'm sure you had some lectures or reading classes or whatever where you discussed objects similar to what I'm going to say. So let's start with Betty's side again. Now for that we do the following trick. With every singular term or irregular term, we associate a real analytic curve maybe I should change it because I is reserved, so then xj, and I restrict this to this small circle. Again, I'm explaining it in the non-coordinate free terms, but it can be said. So it's a map of the small circle under this, so it's a sort of a closed circle which I would like to put in the neighborhood, small neighborhood of my singular point. So, and I have many of them. Each singular term, each alpha, gives me a closed analytic curve, which is some kind of also a circle, G alpha, like that. And so I can take the conormal bundle to each of these. And since every circle is co-oriented, so this conormal bundle is just a cylinder, and I'll take just upper half of it. It's positively oriented conormal bundle. So
I'm confused where your curves live. So they live
in the space. Okay. Again, let's think. They live in the space of of jets, but let's think of them as small circles on X on the curve. Then the conormal bundle lives in the cotangent bundle to the curve, and if I take here, say, real part of the symplectic form, then it's a conic Lagrangian, non-compact conic Lagrangian. And I have many of them, so it's a collection of them. So I can take the union of these Lagrangians, and I would like to add the zero section if I'm interested in the local systems only, not in the all holonomic D-modules. Then I will add zero section minus the union of small disks. So that's a picture for a single point. I remove some very small disk, so it's essentially something punctured, and I have this bunch of cylinders, and I take the union of all this. So if, of course, since the zero section is Lagrangian, it's still some Lagrangian. It depends on everything of this CG alpha, on this collection. All right, and so this is an object of whatever version of rapt Fukaya category you'd like to consider, but even before we're going to rapt Fukaya, we can consider the category of constructible sheaves on X with a singular support which belongs to this Lagrangian. So that's a category which stays on the Betti side, and this is just a reformulation of Betti side of Deligne-Malgrange. If you look,
So these Lagrangians so far, they only depend on the formal decomposition.
these Lagrangians, they depend on the singular terms. Yes, yeah. It doesn't mean that they are formal, they are honest Lagrangians, but they depend only on singular terms. Yeah. But by Deligne-Malgrange, we know that this is enough. It determines everything.
How is the filtration encoded in here?
This is not the filtration, Mohammed. It's a Betti side. You'll see the filtration on the Daram side.
But wasn't there filtration on the Betti side? We had local systems on the server.
You mean how these it's a good question. It's not visible at the finite distance. It's visible at infinity. You should look at the contact boundary at infinity.
So this J's and alphas. So one of them is the punctures, right? J is the puncture.
Yeah.
And then alpha is.
It's just index which enumerates this curve. This curve.
Riemann-Hilbert description.
Yeah.
Right. Okay. But this one, and then you just take the conormals.
Half of them.
But how does it know? So there should be some growth condition.
But it's already here.
I think the claim somehow is these only depend on the formal decomposition, but if you take a random Lagrangian in the Fukaya category with this singular support, then you should be able to read off the Stokes filtration on S1, maybe by looking at
No, but in terms of Fukaya, it will be a subcategory of whatever Shenden, Nadler, Zaslov, Treumann, I mean, this version of Fukaya, which is generated by this. So this is a generator. So when you start to compute kind of Homs between them, probably you know this another picture when you consider these curves placed on the cylinder itself. Yeah. Then when you have these two curves on the cylinder, so then their interaction, this Stokes whatever data, they are visible directly, because the intersection points, it's exactly the points where two real parts coincide. So if you draw the vertical array, so this vertical array gives you this non-canonical splitting of the Deligne-Malgrange filtration. When you approach the intersection point, and when you go on the other side, what was below now above, and so you have a Stokes automorphism. Yeah. Okay. So then again, so that's what I've said, that this is a category with just equivalent to this, and this is say, let's call it just to name Shende, Riemann, Zaslov, Fukaya. In fact, it's better to work with a wrapped Fukaya, as kind of a more general story says. Take an honest wrapped Fukaya and consider finite dimensional modules over it. So this is a more appropriate framework. So anyway, this is a Betti side. Now let's discuss the de Rham side. So the Betti side is essentially kind of topological, if you like, or symplectic, whatever. It does not depend too much on algebraic geometry. Now the Rham side, on the de Rham side, we start with a cotangent bundle of the curve, but since we have marked points with some additional data, like these irregular terms, so then our final variety will be different. And basically, what we will do in order to, okay, what's the point? The point is that if we have a spectral curve, if you have an irregular term, then we can, say in coordinates, we can draw a spectral curve, kind of a germ of a spectral curve, which near the singularity goes to infinity, which is not good, yeah, because then we have to remove this vertical fiber. So instead of this, we take the fiber-wise compactification of the cotangent bundle. So every singular point gets its copy at infinity, and start to make blow-ups. A sequence of blow-ups. So these blow-ups, kind of details of this story, it's not very difficult, but just in case, we work it out with Maxim on the paper on wall crossing structures. But the point is that we make blow-ups of this in such a way that in the end we keep only those divisors, exceptional divisors, at which the pullback of the standard form on the cotangent bundle has poles of order 1. So the point is that if we have a spectral curve here which behave with not a nice way at the given point, has a pole of order whatever m, then after a number of blow-ups in this blown up surface, let's call it T star of x log. It's not a compactification, it's just a partial compactification of the cotangent bundle, which we call log extension of the cotangent bundle. And on this log extension, the spectral curve intersect this log divisor transversally at finitely many points. So then it's indeed a nice spectral curve, but not in the cotangent bundle, but in the Poisson surface. In fact, in this spectral curve, in the Poisson surface. So if we have, again, if we have a spectral curve,
Repeat the definition of the spectral curve. The one attached to one irregular.
So, okay, so this is a definition of a spectral curve. Let's make this sequence of blow-ups and obtain the log extension. Then the spectral curve is a curve, is, effective divisor in T star of x, such that it's proper when we take the closure of its proper transform in this log extension, that it is compact and does not contain entire component of this log divisor.
You started with the differential of those.
It was a motivational. It was a motivational part. If you have a Higgs field with a Higgs bundle with a Higgs field which has a regular singularity, then you can naively draw the curve which I've just erased. Yeah, well, standards, but okay. Then it will go to infinity. But when we do these blow-ups, then we get a spectral curve, is called, it's a definition, spectral curve, if, all right, so then this is a Poisson. Again, this is a Poisson surface. It's not symplectic. It has an open symplectic leaf. Everything is complex, of course. So it's a complex Poisson surface. The Poisson bracket vanishes at the boundary with order 1. It exactly means that symplectic structure has poles of order 1. All right. So then this is a geometry which we need.
If you have just regular singularities, and you would keep the ordinary tangent bundle.
So there are two possibilities in this case. I can do the blow-up once, but then contract the cotangent fiber. So then it's basically I keep the same. Yes. So I take, like log cotangent bundle. No. But I mean, to be consistent with the general story, I should do blow-up at least once. Okay. Now, again, what do we have? We have a Poisson surface. This log extension. Inside we have an open dense symplectic leaf, which is isomorphic.
P is T star x log that, or P contains it?
This is equal.
Okay.
Yeah, it's equal. All right. Now let's look. So this. Let's look at the algebra of functions in this symplectic leaf. So it has a natural filtration. This is a filtration by the order of poles in this log divisor. And this filtration plays a role I mean, this growth plays the same role as the growth of symbols of differential operators at infinity. So now the claim is that there is a non-commutative algebra let's call it, I don't know, quantum, though some people object, over in fact over polynomials in H, but let's take germs of analytic functions at H equals 0 with filtration which satisfies some properties. Let me say in words because there is not too much time. So the modulo H, which means that if we place H equals 0, this story reproduces this one. This is most. So it reproduces this algebra with its Poisson bracket. So then it's quasi-classical limit is this story. The filtration corresponds to this filtration. Now, the only thing that this filtration of this non-commutative algebra, in terms of the filtration, some modules over some, not over complex numbers, it's not a field. And this filtration splits, it's a filtration by free modules over this ring, and it splits. It's in the case when this is just a ring of formal series, this was proved in Maxim's paper around 2000. He called it semi-formal deformation quantization, because it's better than formal in a sense that we do have some control. Yeah, if we are over something where we can fix the Planck constant, then what we get a non-commutative algebra with filtration, and now we can repeat the story which we played with D modules. We can consider modules of finite type with a good filtration with respect to this one, and we can define holonomic modules in this way. So then have category of holonomic DQ modules.
If one take different finite value of F, does one get isomorphic algebra?
Yeah, yeah.
Thanks to the
Yeah, non-zero, of course.
Yes, sure.
Yeah, yeah. This is true. So then, this category should replace this long ago erased category of connections. With singularities at fixed points and with prescribed irregular terms. Now here we can see, if you look a bit carefully with a magnifying glass, we can see some pieces of this formal classification. In fact, we can see it at all this formal classification. For this we should take a component of the log divisor and look at the formal neighborhood and look how this algebra look in formal coordinates. So this is just because it's the symplectic form has pole of order 1. Here it has a coordinate. here. So we can take a coordinate, one along the divisor, one transversal. We can complete along the divisor and look how this algebra behaves. And so we'll see all these pieces of formal classification of Hokuhara-Level-Turiten just here. So for example, if we had something in coordinates something like this, then in the quantum level we will have something like this, yeah, the algebra where x hat are no longer commutative variables. All right, so then reformulation of Deligne-Malgrange, Riemann-Hilbert is that these DQ modules, holonomic DQ modules, let's put h equals some non-zero number. This category is equivalent to this Fukaya subcategory of the category of cotangent bundle, Fukaya of cotangent bundle, generated by this big conic Lagrangian, which I described previously. All right, so this is a reformulation. Yeah, so it takes almost all time just to reformulate. And let me say in a couple of words what should be in general. What's the natural generality for this story? We should start with a complex symplectic manifold in general. Symplectic. And choose, it's an additional piece of data, this log extension. Log extension, it's exactly the Poisson manifold such that the complement is a normal crossing divisor where the symplectic form has poles of order 1. So the example which I will use next, it will be C star square.
M would be affine?
Well, it's, yeah, I mean, a priori I do not require that M log exists, so it doesn't have to, but in practice, yes, it is affine. Yeah. So an example is C star square, then I take any toric compactification and then remove pairwise intersections of the toric divisors. So the form here is the standard one. Yeah. All right. Maybe since I do not have, actually, Paul, you're the boss, do I have any time?
How much do you want?
I mean, should we negotiate? The lunch is coming, so can I?
The lunch is until 1:30.
Ah, okay, good. So I'm not hungry anyway.
10 minutes is fine.
10, okay, good. Okay, so let me, instead of just saying general words about general story, which I do have, let me just consider the second example. Yeah, maybe it will be kind of more interesting. All right, but just to remember that in general we can do it in this generality. All right. Let's consider. All right. So it's a bit change of plan. Example 2. Let's call it Q Riemann-Hilbert, and Q because the algebra which we will be talking about, it's a quantum torus. It's algebra with two, let's say, inversible generators and one relation.
Do you have written on that?
We'll see now. Okay, so yeah, I will. So this is a replacement of the cotangent bundle in this case. Yeah. So then consideration, they correspond to looking not at differential but rather at difference equations. Something like this. So Q is a complex number. I don't know. We can take it like this. There is a theory of holonomic modules with this algebra, actually in any dimensions. So we can look the Bernstein filtration.
Did you describe what X hat and Y hat was in terms of?
Okay. X hat is multiplication by x, and y hat is a shift. F of x goes to f of qx. Maybe up to changing q to q minus 1, but so there is a filtration on this of this algebra by the total degree. So it's a Bernstein filtration. So then we can consider modules of finite type with a filtration which is good. So holonomic one stat because it's C star. I can put any n. Maybe I should remove this because I will not consider any n. So holonomic Q module. So it has filtration with growth like this. I put 1 here because if I have n, it will be n. But now I'm removing it. So it has linear growth with respect to the index. So then we have a category of holonomic modules. It's an abelian category. Holonomic AQ modules. Now there is an analog of the formal classification in this story, which means that the difference between C star and the general curve is that this dilation by Q has only 2 fixed points, so singularities can be placed either at 0, 1 compact, or at infinity. So therefore there will be just Stokes data consisting of 2 sets. Now if we are, say, at 0 and want to classify formally this holonomic whatever, again there is a torsion, there is a possibility of not only for difference connections but also for it's even a little bit more interesting here. So there is a possibility for holonomic modules which are supported on the geometric progression. But anyway, locally at 0, let's put it x equals 0. So this category splits into the direct sum. Let me first write it down, then I explain the notation. It's an analog of Fukuhara-Levelt-Turitian. Let's call it C like this, too many C's. So the difference between difference and geometric and differential case is that we do not have exponential growth. It's only polynomial. So the analog of irregular terms is just rational numbers. Or from the symplectic point of view, it's better to think about every rational number as an array. In R2, this is 0. This is an array with the corresponding slope. So then formal classification gives us a collection of rational arrays in R2.
It's a semi-simple category.
Formally, yes. Now, these are basic modules which correspond to, better to say, to different equations of the following type. It's some constant, I don't know what constant, say b, xa, f of x. This is some matrix. And this is a piece which indeed corresponds to a equals 0, b equals 1, but it's in fact analog of the regular singularities. It's an analog of regular singularities, which means that there is a lattice in the module which is preserved by this y hat, by multiplication by q. So then this is a regular part, this is, if you'd like, irregular part. And this is a formal classification.
Can you tell again what is this C over B?
These correspond, these are these modules of the quantum torus in the formal sense, which are given explicitly by this, and this is a constant matrix. This is constant. Just simple kind of singularity of this type, x in the power a. In fact, it can be rewritten.
Give a parameter,
No, that's the point. In this story, there are no moduli.
this constant.
No, but this it's inside. It's for all possible C's. So it's whatever, or B for all possible B's. It's all in this category. Yeah. All right, and now I can formulate the Q Riemann-Hilbert and then explain its symplectic meaning. No. All right. Sorry. Okay, good. All right. Maybe I'll send. No. Oh, wrong choice. Okay, so let me practice a little bit. Okay, that's the right one. So now the Q Riemann-Hilbert. Before I formulate this Q Riemann-Hilbert correspondence, let me give one general definition, which actually can be done in any general triangulated category with a stability structure. So suppose that we have an object and some, let's take first let's consider abelian category with a stability function. So abelian category with Bridgeland stability function. So it's a definition of an anti-Harder-Riemann filtration. Maybe I should skip the definition because it's obvious. So it's a filtration of an object such that consecutive quotients or cones in the triangulated sense are semi-stable, and their slopes or arguments, it's better, instead of decreasing like in Harder-Riemann, they're increasing. So it's not canonical, therefore, differently from Harder-Riemann. So anti-Harder-Riemann filtration of E. So they can be. It's non-canonical.
You wrote arg. That means the image of the stability function.
It's argument of the central charge applied to this semi-stable object. So every semi-stable object has its argument. So and the sequence of arguments increases. So now the theorem. It's Q Riemann-Hilbert. The category so first a general result, which does not take into account this singular data. The category of holonomic modules of the quantum torus is equivalent to the category of coherent sheaves, not constructible but coherent sheaves on the elliptic curve, and these sheaves end out with two anti-Harder-Riemann filtrations. So the point is that these rational slopes, one at 0, collection of this rational, let's call it Lagrangian fan, because in bigger dimension it will be a collection of polyhedral Lagrangian cones in R2n. Yeah? So this collection of rays, which is determined by the slopes, let's call it Lagrangian. So we have two Lagrangian fans, like two collection of rational rays, one for 0 and one for infinity in the case of C star. So, and these are slopes, if we place them on the plane, so they should be thought as slopes of these quotients, of semi-stable quotients. All right.
So coherent sheaves on what?
On the elliptic curve, this is a definition. C star modulo Q in the power Z. I wish I had a bigger blackboard, but it's C star mod QZ. Q is the same as in the definition of quantum torus. All right, so of course now I should explain how this picture fits in this bigger picture with the toric compactification of C star square, for which I absolutely do not have time. Maybe let me say why we have coherent sheaves on the elliptic curve instead of constructible sheaves. Because this result is not really in one dimension. It's essentially it's a reformulation of the result from the paper by Ramis, Salol, and probably Zhang of 2009. They studied different, well, one is Ramis, that's for sure. They studied difference equation, they studied local classification, so very much of what I said is just reformulation of what they did. But in higher dimension, there was not even a conjecture of what should be Riemann-Hilbert. And in the higher dimensions, which means that we have C star n where differential operators, difference operators live. So we have this type of algebra where I and j from 1 to n. So the analog of the cotangent bundle is this one. Now instead of rays in R2, we have a polyhedral cones, Lagrangian polyhedral cones in R2n. So we have a fan. Now this fan defines a T structure in the derived category of coherent shifts on the power of this elliptic curve. Basically, we should look at the Lagrangian plane, these are cones of full dimension n, Lagrangian. Yeah? We should look at the plane which is generated by this cone, and then think of it in terms of Fourier-Mukai. If it's just a coordinate plane, then the T structure consists of coherent shifts with zero-dimensional support. Otherwise, we take the action of the group SP to n to make it the standard coordinate, and this is a T structure. And this should be done for every element of this Lagrangian fan. So then the general formulation will be slightly different. The appearance of these stability structures in dimension 1, it's misleading. But in general, we have this story, and this R2n is not very surprising. If you think naively of the Fukaya category of C to n, yeah, if you factorize it, yeah, as whatever, like product of the torus with R to n, yeah. So, and think of the Fukaya category as a tensor product of these two things, then this collection of rays, or this collection of cones, is indeed a collection of Lagrangians in the Fukaya of this tensor factor. So then the message is that these Fukaya categories are very much the right language to speak about Riemann-Hilbert in more general framework. So, yeah.